Welcome to this lecture series on groups. Previously, we have seen a motivation for the notion of a group, and in the previous lecture, we looked at the notion of a binary operation. In today's lecture, we will see a proper definition of a group and some examples and non-examples. So let's proceed. Some problems for practice. And now let us get started. So what is a group? So just like when we define a vector space, we say that it is a quadruple where V is a set, F is a field, plus is a binary operation on V, even though we do not call it a binary operation, but that's exactly what it is. And this dot is something, we know what that is. And so on and so on, and we demand that the plus and the dot satisfy some axioms, some properties. Similarly, a group is a pair. It's a pair where the first entry of the pair is a non-empty set, and the second entry is a binary operation on that non-empty set, such that certain properties are satisfied. The first property that we demand is associativity, which means what? Which means that star is associative. We discussed the definition of associativity of a binary operation in the previous lecture, but just to recall, it means what? It means that this element of G is equal to that element of G for all A, B, and C. So it doesn't matter how you put the brackets, you will always get the same answer. We mentioned that this is a very desirable property of any binary operation. Any useful binary operation better satisfy this property. Okay, second property we demand is the existence of an identity element. What does that mean? It means that there exists an element E in the set G such that it behaves like identity. Under this operation star, it behaves like an identity element in the sense that it doesn't disturb what it operates with. Just like the multiplicative identity of the integers doesn't disturb what you operate it with under multiplication, or the additive identity of integers doesn't disturb what you operate it with under addition. The operation here is addition, it's the additive identity. Similarly, we are kind of generalizing that notion that the element E is behaving like the identity. It is not disturbing what you operate it with. Okay, what do I want to say about this? Do I want to say anything more? So here is an exercise which we will do in the next lecture properly. But for now, you can take it as an exercise. Show that the identity is unique. Show that there is only one such element. Show that there is a unique such element. What am I trying to say? I'm trying to say that here we have only demanded the existence of such an E, but it follows that there is going to be exactly one such thing. There cannot be two different things which have the same property. So that's an exercise, but in the next lecture we will write down the full details. And lastly, inverse. So here we demand that for each element x in G, there is an element y in G such that x star y equals y star x equals E. And this makes sense only when I've already proven this. So maybe I'll write a proof because I'm using this fact, so why not write a proof? So uniqueness of identity. Identity is unique because if E and E prime are identities, so this thing is called an identity. Anything which satisfies this property for all x, here I should have written for all x, is called an identity. So suppose we have two different, or at least two different identities, then by definition, what is E star E prime? E star E prime, if you think of E prime as x, then E star E prime is E prime, but if you think of E as X and E prime as the identity, then you get E as your answer. So this is also equal to E. That's it. So in linear algebra also, we show the uniqueness of the additive identity of the vector space. And when we discuss fields, we show the uniqueness of the multiplicative and the additive identity of a field. It's a very similar proof. Okay, so that's that. And yeah, so now when we talk about inverses, we are demanding that for each x in G, there is some element y in G such that this equation holds. Okay, and here I will give you an exercise. Show that each x has a unique inverse. So here y is called an inverse of x. For any element x in G, y is called an inverse of x. If this happens, we are only demanding that every element has at least one inverse. It is another matter that there will be exactly one inverse by virtue of these axioms. So that's the definition of a group, but what does it have to do with symmetries? So, as we said, you should think of G as the set of all the symmetries of some object. That object is hidden from view, but that is how we should think about it. Now, what does associativity say? Before we get there, what is this star? What is star to be thought of? When G is the set of all the symmetries, what is to be thought of as A star B? So A is a symmetry, B is a symmetry. You should think of them as things which act on the object which is hidden. So if you apply B to the object, it could be some geometric shape, like it could be anything. It could be anything which admits some symmetries. So you should think of B as some operation on this hidden object to produce another configuration of that object. So yeah, I should have said that. You should think of every symmetry as acting on the configurations of the object, right? So you have some object like the equilateral triangle, and it has in some sense various configurations, whatever that means. I'm talking very abstractly. So every element of G should be thought of as an operation or an operation on the set of configurations of the object. And when you do A star B, you just think of it as a compound operation. So here you have your object or a configuration of the object. You apply the symmetry B to it, and then you apply A to it. What we are saying that star is a binary operation exactly says that this compound operation is also a symmetry, because A star B again lands in G. G was supposed to be the set of all the symmetries, and A star B, therefore, since star is a binary operation, A star B will again land in G. It is only saying that a compound symmetry formed out of two symmetries in G is again a symmetry, is another symmetry. So applying two symmetries in succession produces another symmetry is what the binary operation nature of star has captured. Now, what does associativity capture? It says that if you have three symmetries, let's say, and either you can think of this as a symmetry, meaning first you apply this compound symmetry on a configuration and then you apply A on the resulting configuration. Or you may think of it like this, that first you will apply this guy to a configuration and then you will apply this compound symmetry to the configuration. It will not give you any different answers at the end. So that's what associativity is philosophically. Identity, what is it trying to capture? It is trying to capture that the do-nothing operation is a symmetry. You have your object with you, you do nothing to it, that is also counted as a symmetry. That is all that this is asking, philosophically speaking. And inverse is that every symmetry admits something that nullifies its effect. Just like in equilateral triangles, you can rotate by 120 degree and then you can rotate back by 120 degree in the anti-clockwise sense. So that's what inverse is asking. Having said all this, the philosophical motivations or the philosophical interpretations may not be immediately extremely clear, and that's okay. They will be clear with time. For now, this is an abstract definition for which we have some idea as to where this is coming from. We are not completely lost. It is not some arbitrary thing written on the slide. We have some motivation for studying such a pair. One could have defined some arbitrary properties here, but why would they be interesting? Why would you study them? Here at least we have some idea why we should study them, and that's good enough for now. We will foster our understanding by means of concrete examples. The definition is abstract, but in mathematics, when you want to understand something, especially some abstract object, you should look at a bunch of examples. Work through examples. I can't stress this enough. Work through examples. One should not fall into this trap of thinking that I know the abstract definition, then what is the need for looking at anything concrete? I know the most general thing that there is to know, and I can apply logic, so why should I bother to even work with examples? Well, to build a relationship with an abstract concept, you need to know some examples. Otherwise, it will be some bunch of symbols and some computer hacking away the symbols and doing symbolic algebra. That is not what we want. We are humans. We want to understand things. We want to have some intuitive grasp over things, right? Mathematics is a meaningful activity, not some formal, dry, boring calculation, right? So work through examples. And this is a general piece of advice, not only applicable to group theory. Everywhere, all mathematics. Okay, now a point of notation. No, this is not a point of notation. This is a definition. A group G comma star is said to be abelian, named after the great mathematician Abel or Abel, I don't know how to pronounce. So a group is called abelian if star is commutative. Which means what? Which we in the previous lecture saw means that A star B is equal to B star A for all A and B in G. And we will look at examples of groups which are not commutative. Those are perhaps the most interesting groups. An abelian group is easy to work with, but those are not really representative of the idea of a group in some sense. Okay, and now for a point of notation, we may use the phrase let G be a group. We may write something like this. This GP stands for group, just an abbreviation. So when we say something like this, we mean that there is a binary operation. I mean, we mean that there is a binary operation, but we do not explicitly mention its name or notation. That binary operation is hidden because most of the times on a given set, you're working with exactly one binary operation, especially in the context of groups. And even if there are two possible natural binary operations that you can work with, from the context, it is clear which binary operation that one is talking about. Just like when we say let V be a vector space, we do not specify the plus and the scaling operation. Similarly here, so this is frequent. Also, if X and Y are elements of G, we just write XY to mean X star Y. This star will be written once we want to emphasize which binary operation we are using, but again, as I said, most of the times the binary operation in question is clear from the context. So this is the notation that we will use, and in fact, the star will be referred to as group multiplication most of the times. This will be referred to as group multiplication. It's a binary operation, but it is natural to call it multiplication because we are notating it as such. The notation here is very similar to that of multiplication. When the group is abelian, it is natural or it is customary to not use the symbol star, but use the symbol plus, so that the abelianness, the commutativity of the group is emphasized. So here symbol plus is usually used instead of star. So I don't know how to or where to write it. Let me just say it. So when your group is abelian, instead of star, you usually write a plus. This plus has nothing to do with the plus that we are familiar with on integers or reals or complex numbers or whatever vector spaces. This is just some other abstract plus. It's just a symbol chosen so that it's just easier to look at. All right, so far so good. Now we want to look at examples. So the examples that we will look at in this lecture are not the most representative of groups. They are examples because they will satisfy the axioms, but not all examples are created equal. But we have to start somewhere to get the feel for the abstract concept. And we will start at with a very lousy example, which is C star. What is C star? C star by definition is those complex numbers. So I'm assuming you know complex numbers, the high school level of complex numbers, you know. Those complex numbers which are non-zero. So that's a set. Where is the group? For the group, for it to be a group, there should be a binary operation on C star, and already we have a conflict. This is star and that star, they are just looking the same. So what I'm trying to say is the binary operation here is the usual multiplication on C star or on complex numbers. So this is a group. C star equipped with the usual multiplication, which I may write as a dot. This is a group. This is a group where star is ordinary multiplication of complex numbers. Sorry, not star. Dot is the ordinary multiplication of complex numbers. A lot of abbreviations in that statement. So why is this a group? Associativity is clear because complex multiplication of complex numbers is associative. But before we even get there, we should at least justify why dot is a binary operation. Is there anything to justify? Yes, there is. Because a binary operation is supposed to be a function from the set G cross the set G to the set G. And the thing is that if you multiply two non-zero complex numbers, you will get a non-zero complex number. So that this dot over here is indeed a binary operation. So this dot is a binary operation. Now we can ask for whether or not these three axioms are satisfied. Associativity is clear because complex multiplication is associative. So this is fine. Identity, well, clearly the complex number 1, which you may even write as 1 plus 0 iota or something, but it is also written as 1. 1 times z is z for all z. 1 times z is equal to z times 1 equals z for all z. So identity exists. Wonderful. What about inverses? Well, if z is non-zero, then this is 1. Right? So very simple to verify these three axioms. Also note that this group is abelian. This is an abelian group, which I don't want to write because there is no space. So fine, we have an example of a group which is abelian. All right. Another example, the circle, the unit circle. So what is the definition? It is, one way to write it as those complex numbers which have magnitude 1. That's the definition. Here I have also drawn a picture. So you can think of this as a subset of R2, but it is better to think of it as a subset of the complex plane, which consists precisely of those complex numbers which have magnitude 1. So it will look like a circle. And this is also a group under the usual multiplication of complex numbers. So S1 comma dot is a group where dot is the usual product of complex numbers. Let me not write that. Again, before we even ask for these three axioms, is this a binary operation? Well, it is, because if you multiply two complex numbers of unit magnitude, you are going to get a complex number of unit magnitude. So it is indeed a binary operation. Associativity follows because of associativity of the usual product of complex numbers. Identity, well, this guy 1 is sitting over here, so identity is also here. Inverse, well, if you take a complex number z, if you have a complex number z, then and z has unit magnitude, then its inverse, namely 1 upon z, also has unit magnitude, and geometrically it is the reflection of z about the x-axis or the real axis. And it is at the same time the conjugate of z. Reflection about the x-axis gives you the conjugate. And it turns out, because z is unit magnitude, the conjugate of z is same as the inverse of z, the multiplicative inverse of z. So the inverse also exists. If we had taken S1 as not of unit radius but of some other radius, then it wouldn't become a group because it wouldn't even give you a binary operation under usual multiplication. multiplying two complex numbers of magnitude 2 doesn't give you a complex number of magnitude 2, it gives you a complex number of magnitude 4. So it is important that this be unit magnitude here. Okay, so this is a group. I don't want to write anything down here to explain why this is a group. I have said it in words. One thing we may observe is that everything here is an element of C star. So it is in some sense contained in C star. Whatever. So let's proceed. Next example. Suppose n is a positive integer and we define a complex number zeta n as such. Clearly, zeta n has unit magnitude, and in fact an alternate way that you must have seen somewhere is alternate way to express zeta n is to write it this way. But I prefer this notation because exponentiation of complex numbers is a sensitive matter. That is something that should be done in complex analysis. Anyway, let me explain that via picture, although I'm assuming that this much complex numbers you know. So if n were equal to 6, what is zeta 6? It is the complex number on the unit circle because this has unit magnitude. So it is which complex number on the unit circle? It is the one that makes an angle of 60 degree from the positive direction of x-axis. And as you exponentiate it, meaning take square, cube, power 4 and power 5 of this particular guy, you will cycle around. Since n is equal to 6, once you raise this to the power 6, you get 1. So this is same as zeta 6 to the power 6. But for every other power, these are the things that are drawn. In general, the picture will look very similar. It's just that instead of zeta 6, you will have zeta n, and that will make an angle of 2 pi by n from the positive direction of the x-axis. Okay. So where is the group? What is the group, etc.? Well, let G be equal to all powers of zeta n. You could write an integer, but you could also just write natural numbers and nothing is going to change. So this is our definition of the set G. Note that this is a finite set. This set is nothing but zeta n to the power 1, zeta n to the power 2, power 3 up to power n. This last thing is nothing but 1. So this is our set, and the operation, the binary operation, is the usual multiplication of complex numbers. Then this is a group. Well, the fact that this is a binary operation is clear because if you multiply two things of this sort, you will get something of this sort. So that is easy to check. So this is a bona fide binary operation. Associativity follows because the ordinary multiplication of complex numbers is associative. What else? You have identity because 1 is certainly a part of this set and 1 will act as an identity of this guy. And lastly, inverses. Well, there are multiple ways to see inverses. One way is the following. If you have zeta n to the power k is some positive integer, then zeta n to the power minus k is an element there. It may not look like it because minus k is nowhere to be seen in the exponents, but you can write zeta n to the power minus k as that. So if k were less than, if k is between 1 and n, then this number is between 0 and n minus 1. So this is a part of that set. Okay, so just check that. If you pick anything from this set, there is an inverse to it under this ordinary multiplication, namely this guy. Right? So just verify. And that gives an example of a group. This group is also, of course, abelian. Maybe I should give a notation. So this group is also represented by, we may represent G as that. This is one way to represent it, but forget about it. So this is an abelian group. So just like S1, the example in the previous page, S1 was contained in C star. This thing that we just discussed is contained in S1. So there is this descending chain, so to say, whatever. Okay, next example. This is a particularly lousy example. We have the set of all the integers and the ordinary addition. We claim that this is a group. Clearly, this is a binary operation because if you add two integers, you get an integer. Associativity of this addition is clear and very difficult to explain. That holds. Identity. What is the identity of this group, if at all this is a group? So the question should be, what is the identity, or is there an identity in this set under this binary operation? There is, and that identity is the usual 0. If you add 0 to any integer, you get the same integer back. Right? So the identity exists. And inverse is, if you pick an integer n, then minus n is an additive, is an inverse under this usual addition. Right? N plus minus n is 0. So this is a group. This is also an abelian group. So far, all the examples have been abelian. And I think the next example will also be. Yeah, so this is now the collection of all the even numbers. 2z denotes, this by definition is twice of n, where n is some integer. So another way to say it is the collection of all the even integers. This is a group, and this is an exercise. You add two even integers, you get an even integer, etc., etc. So this is a group. Again, abelian. And to generalize this thing, nz is a group under ordinary addition, where n is any integer. So what is nz? Nz is just scale every integer by n. And yeah, I drew some pictures here. So this is your set of all integers, and this is twice of z. Similarly, you can draw a picture of this. It will look exactly like any of them. These two are exactly the same pictures in the sense that if you look from far away, this guy will look like that guy. Anyway, there is a group theoretic way in which you can say that actually these two examples are the same, that we will look at later. It is called isomorphism. All right, so let's proceed. Another example. So this time Z2 with your, well, what should I say? This is in some sense the ordinary addition. So let me define it. What is Z2 first of all? Z2 is all the ordered pairs with both entries integral. And how do you add things? So if you have a plus b and x plus y, the way you add them is entry wise. This is how you add them. So this is a definition, and this is nothing new to you. This is how you add things in R2. Z2 is after all a subset of R2, so just add the way you add in R2. Think of them as elements of R2 and add them. It's just that if you add 2 points of Z2, you will also get a point in Z2, because this will be an integer and that will be an integer. So this is clearly a binary operation on Z2, and you can easily verify that this is a group. So exercise that this is a group. This is also abelian, but let me show you a picture. This orange thing is your 0, 0, the origin, and this is the identity of this group. And if you pick an element here to invert it, if you're asking what is the inverse of this guy, just reflect it about the origin. This guy will be the inverse, right? If you pick that particular element in Z2, what have I done? If you pick that particular element in Z2, just reflect it about the origin, you will get the inverse. And these two things are inverses of each other. Okay, great. So very simple. I'm sure all of this is very intuitive. This is a slightly more interesting example. So Z mod nz, I don't want to recall this. We dedicated enough time on this object. So this under its addition, so the way you add things here, again, I don't want to spend time on it. And this is also a group. So associativity, first of all, this is a binary operation that I'm not going to justify. You know this. by now. The associativity is also something that I'm not going to justify. What about identity? Well, the remainder class of 0 is your additive identity or the identity of this group. And for inverses, if you have the remainder class of x, the remainder class of minus x will be the inverse of it. So the formal justification is an exercise, and this group is also abelian. For a picture, here this is a picture of Z mod 5Z. Here, to be very precise, I shouldn't have written a 0. This should have been the remainder class of 0. This is the remainder class of 1 and so on, but it is customary to not decorate too much. So this is a picture for Z mod 5Z. The picture is self-explanatory. You add 1, you add 1, you add 1, you come back ultimately. Anyway, and now another very boring example, R2 under its usual vector space addition, the coordinate wise addition is a group exercise. This is also abelian. Everything so far has been abelian. Alright, next. This is slightly more interesting, but this is just a cousin of C star. In fact, this is a simpler example than C star. Perhaps this should have been the first example, but who cares? So R star, what is R star? You can guess. R star is this set, all non-zero real numbers, and dot is ordinary multiplication. Usual multiplication of real numbers. We claim that this is a group. This is clearly a binary operation because if you multiply two non-zero reals, you get a non-zero real, and everything else is an exercise. For the multiplicative identity or the identity of this group, it's the real number 1, that is the identity of this group. This is also abelian. Okay. This is again slightly more interesting. So this time we are saying collect these kinds of numbers where you are allowed to select only rational numbers in place of a and b. So for all possible choices of rational numbers a and b, you get all possible such numbers. You collect them in a set, but again, there is another condition here which I forgot to say about. A and b cannot both be 0. So the 0, the real number 0 is not here. Okay, this contains only non-zero things, but not all non-zero things, these kinds of things. And then we are saying that even that is a group under ordinary multiplication of real numbers. This is ordinary multiplication of real numbers. So to check that this is a binary operation, why is it a binary operation? Well, if you multiply a plus b root 2 with, maybe I'll take more space above. If you multiply a plus b root 2 with x plus y root 2, where a, b, x and y are rationals, what do you get? You get ax plus 2by plus root 2 times, or maybe I'll write it as something times root 2. What is that something? That is bx plus ay. So clearly, if you multiply two things of this sort, you get another thing of that sort. Also note that this cannot be 0. If this and that are non-zero, then this also cannot be 0. Right? So justify, very simple. So this is a bona fide binary operation on this set. And now we need to worry about, well, associativity is clear because ordinary multiplication is associative. Then we need to think about identity. Identity is clear because 1 plus 0 root 2. 1 plus 0 root 2 is just 1, and that is here. That is available here, and that acts as the identity of this group or this set so far, not a group. We are trying to prove that it is a group. So the identity also exists. Perhaps the existence of inverse is a little bit interesting. Note that if at all there is an inverse of a plus b root 2, if you have this element a plus b root 2, if at all it has an inverse, it has to be this guy. There is just no other candidate. So we need to show, what do we need to show? That this can be written in this way, meaning you can find rational numbers x and y such that x plus root 2y is this number, but then you use the rationalization trick because you rationalize above and below. You multiply it like this, and note that this is valid because this cannot be 0. If this were 0, since a and b are rational numbers, the zeroness of this will force that both a and b are 0, but not both a and b are 0. That is what we have already started with. So this is legitimate. And now if you just work this out, you get this is a minus b root 2 on top and some rational number, non-zero rational number at the bottom. Why the bottom is non-zero? Simply because one way to say it is that root 2 is a rational number. Sorry, root 2 is not a rational number, or simply this was non-zero and that is non-zero, so their product cannot be 0. And clearly this is a number of that sort because you can write this as a upon a square minus 2b square minus, or I'll write a plus and then a minus b upon this thing times root 2, and there is no space. So anyway, I'm sure you were able to do this by yourself. Okay, I think the next is very interesting. Yeah, quaternions. So quaternions, well, first of all, I have this set of symbols E bar, I bar, J bar, K bar. These are just 8 symbols. So the set Q, or Q8 as it is usually written, Q8 is defined as this set. This is a set of 8 different elements, 8 different symbols. Okay. These are 8 abstract symbols, and how is a binary operation on them defined? Via this table. So this is called a multiplication table or an operation table maybe. So how do you read it? We are saying that E star E is E star E bar is E bar, E star I is I, and so on. J star J bar is E, K star I is J. So just to read it naturally. So there is some binary operation defined on it, and it is a bland exercise to verify that this is a group. Everything before this example was an abelian group, but this example is not abelian. So why is this a group? Well, just verify. I can't say anything about it. You can just verify if you have a lot of time, or you can believe it. How do you compute? Say something like this. I, J, K, J. These are elements of this set, so you are allowed to product them now because there is some binary operation defined. How do you compute it? Well, you can bracket it this way, ij. So first you compute ij. What is ij? You go to I, you go to j, they meet here, so this is k. So the first thing is k, and that is getting multiplied with another k. K, how does that behave? K times k is e bar. So this whole thing is e bar. So finally we have to compute e bar multiplied by j. E bar multiplied by j is j bar. Now, this is admittedly a very cumbersome way, or certainly not a human way of expressing things. We can express the same data by means of a diagram. So what do? We have listed out all the 8 symbols that constitute the set Q8, and the red arrows denote what? The red arrows denote multiplication on the right side by the symbol I. So if you multiply by I on the right side, meaning if you start at k bar and compute this guy, you will get j bar. That is what the red arrow means. And indeed, if you start at k bar and multiply by I on the right, you get j bar. Right? Similarly, if you multiply by right side by I, the element j bar, what do you get? J bar, multiply on the right by I, you get k, and that is what the diagram also shows. So the same data can be captured by a diagram. So the blue arrows and encode multiplication on the right by j, red arrows encode multiplication on the right by I. We could have drawn more arrows, like what about multiplication on the right by k? We haven't drawn those arrows because we do not need to. Why? Let's see why. Let's try to compute this guy using this diagram. So what is k first of all? This multiplication by k is what will trip us, but how do you get k? How do you reach k? Suppose you start at identity, how do you reach k? You follow the red arrow and then the blue arrow. So you can think of k as red arrow followed by blue arrow. Or in other words, k is nothing but I or E times I times j, which is just I times j. So the diagram tells us that k is I times j. So we wanted to compute I, j, k, j, but we may write it I, j, I, j, j. So this is one way. Once you have parsed it in the world of ij only, then you can just follow the arrows. So I'll start at I. Now I'm multiplying I by right on j. Multiply by right on j is just following the blue arrow. So I follow the blue arrow. Now I'm multiplying the result by I on the right. So I'll follow the red arrow. Then I'm multiplying the result on the right by j. So I'll follow the blue arrow. And then finally with the j, I'll follow the blue arrow. I end up at j bar, and that is what we got here also. So that is one way, or there is another way. Just think of k as red arrow followed by blue arrow. You're starting with identity, so applying a red arrow and applying a blue arrow, you can just think of that as k. Now, I'm starting at I. After that comes a j, so that means apply a blue arrow. Now comes a k, so that I have already understood as apply a red arrow and a blue arrow in succession. And now apply j, meaning a blue arrow, so you get j bar. So that is also another way. So any long string of symbols can be computed using this diagram just by following the arrows or by using this table. Of course, the computer is more comfortable here, the human is more comfortable here. I hope this was clear. This is called the multiplication table, and this is called the Cayley diagram. I'm not going to formally define what is a Cayley diagram, but this we might see over and over, and we know what this means. Let's not give a formal definition of the Cayley diagram or the Cayley digraph, also called the Cayley digraph. But yeah, when we say Cayley digraph, it has to be defined with respect to a set of generators, whatever. We will use this phrase somewhat informally. All right. So one more example, V4. This is called the Klein's 4 group. And the previous example was non-abelian. I don't know if I mentioned it, but Quaternions form a non-abelian group. So we have V4. This is how it is defined. So it is a group on 4 symbols, E, A, B, C, and this is the multiplication table. You can blatantly verify that this is a group. And in fact, it is an abelian group. It is an abelian group and very abstract, but it arises out of some very concrete symmetry considerations. What symmetry considerations? Consider this cross-shaped object, but the vertical lengths and the horizontal lengths are different, but they meet at their endpoints. Okay? So this is a rhombus, but we have forgotten about the sides, whatever. You can draw the full rhombus if you like. Okay. So what we will do is, just like when we were motivating the idea of a group, we colored the vertices to keep track of the configurations, quote unquote. So we color the vertices of this cross. Okay. Orange, blue, red, and the mystery color. All right. Now interpret A as reflecting about the vertical line. So A will be thought of as reflection. How do you write reflection? Reflection about the vertical line. So that is how you think of A. And B will be thought of as reflection about the horizontal line. Okay. And I've drawn a dotted segment. So this goes both ways. If you reflect about the vertical line and again reflect about the vertical line, you'll come back to the same thing. So I haven't drawn any arrows, or you can draw arrows both ways if you like. So let's see. If we reflect about the vertical line, then we get this configuration. These blue and mystery color will remain where they are. The orange and the red will flip. And now if you reflect about the horizontal line, the mystery and the blue will shift their positions, but the orange and the red will remain where they are. But what is the combined effect of these two applications? It is just rotation by 180 degrees. So you can think of C as rotation by 180 degree, either clockwise or anti-clockwise, it's the same thing. So C can be thought of as rotation by 180 degrees, and you can easily see that A first, B after is same as B first, A after. So it's an abelian group that way. A square is identity, B square is identity, and so on, and C square is also identity. So A square, B square, C square are all identities. And yeah, so I think we have given sufficient justification for what is going on here. And this is the Cayley diagram of the group. So what is the difference between this diagram and the Cayley diagram? In the Cayley diagram, the nodes are the elements of the group. While in this diagram, the nodes are something else. The nodes are the object of which we are trying to think of the group as the set of symmetries of. My English was off, but I'm sure you understood. Here, the nodes are the group elements themselves. So there is a slight difference, and anyway, I have not defined what is meant by the Cayley diagram of a group formally, so it doesn't matter. This is just capturing the multiplication table in a diagrammatic fashion, so you can check that. Okay, I think this serves as a good example of a good set of examples of groups. And now let us look at non-examples. Right. So the natural numbers with ordinary addition is not a group. This is a binary operation on n, that's not a problem. If you add two natural numbers, you get a natural number. But what is wrong? What is wrong is, first of all, there is no additive identity, or there is no identity to this group, right? Because 0, the integer 0 is not here. If at all anything acted as the identity, it had to be the integer 0, but that is not here. So it is not a group for that reason. Also, inverses are not available. No negative number is here, and if, for instance, 3 were to have an inverse here, it would have to be -3, but that is not available here. So it is not a group for that reason. What about this guy? If you multiply two non-zero integers, if you multiply two integers, it is going to be an integer. So this is a binary operation on Z, but what about, well, associativity is there, but identity is also there because 1 is here. However, inverses are not available. 3 cannot be inverted in this uh, world, because if 3 were to have an inverse, then it would have to be 1/3, but 1/3 is not an integer. So this doesn't qualify as a group. What about this guy? X is some non-empty set. Power set of X is, you know what it is. And unioning gives a binary operation on power set of X, but this is not a group. Associativity is not a problem. Identity is not a problem because the empty set acts as identity. What about inverses? Well, there is no way to kill a subset. Suppose you have a set A which is non-empty. You can't union it with anything to give you the empty set. The empty set is the identity here, but you can't union a non-empty set with anything to kill it. There is just no way. So this is not a group for that reason again. Matrix multiplication. Matrix multiplication doesn't give you a group. If you take your set G as all n cross n matrices over a fixed field, over a field F, then this is not a group under matrix multiplication, simply because matrix multiplication, well, inverses would be a problem again. Identity is here because the identity matrix is acting as the multiplicative identity, but inverses would be a problem. For instance, the all zeros matrix doesn't admit an inverse. So this is not a group again for the lack of inverses, and this is also not a group. As we saw, for instance, the remainder class of 0 cannot be inverted. So this is not a group for any n. So there are important non-examples of groups. Groups cannot capture everything, as they shouldn't, because they are supposed to be the symmetries of some object. Okay, so yeah, with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.